Kia ora, everyone, dear fellows and professors, President and Professor Wilson. It's a great honor for me to present some of my research on the ammonium combustion. So it's a beautiful day, it's really warm, but my presentation will concern with burning something and generating smoke, okay? So, can you? Okay. So the background and the motivation for why we need to conduct some research on the ammonium combustion. This is what is happening and due to the global warming and climate change. So during the past 150 years, so human beings burning the fossil fuel with millions of tons of producing the CO2. And now the CO2 in the air is affecting everybody. And in Christchurch, it happened twice. We have the wildfires. And in Auckland, they have the cyclones. So it happened, many disasters are happening. So the key contributor is the CO2. And in the future, what we can do is to minimize the CO2 emissions. So the National Party set the target we're trying to reduce by 2050. So we have produced net zero CO2 emissions, but that is pretty ambitious. There was supposed to be by 2025, there should be 50% of reduction of CO2 emissions, but what is happening in Europe and Asia, so now it seems to be too ambitious to get the target done. So we're looking for something alternatives instead of the fossil fuel. The fossil fuel, the key component is hydrocarbon. So we're trying to replace it with something new, not producing any CO2. So what we have two candidates available. One is hydrogen, another one is ammonia. Okay. So don't be scared by this table. So you can only compare the values, and I will introduce the general ideas. So the values is telling us, okay, so the greater values is indicating this is more efficient to be burned and producing more power. And what you can compare it is the ammonia one. So the ammonia with the minimum values. So that means it's difficult to burn, but on the other side, it's safe. Okay, compared to hydrogen. So hydrogen is highly flammable and highly explosive. So methane and propane, we probably, you at home, you're cooking, so with methane or propane is good. But those will produce CO2, so there are only two candidates for us to use. There is another background story related to ammonia is ammonia every year globally. The countries produce and treated 220 million tons of ammonia. So ammonia, 80% of them are used for fertilizer, and another 20% has been used for plastic and also explosives for some other purpose, okay? So that is ammonia. So ammonia has been widely traded between the countries and the continents. So everything for ammonia to be burned is ready to use. So we have the infrastructure, it's convenient to be transported, it's safe compared to hydrogen. So this is
Could the future of renewable energy lie with a common household chemical? Ammonia might power your cleaning products and fertilize your plants, but it could soon be the carrier for moving energy around the world. Oil and gas, which make up most of our energy supply, can easily be shipped and stored. But renewable energy, which travels through the power grid as electricity, can't, preventing it from becoming a bigger player on the world market. That's why researchers are trying to convert solar and wind energy into liquid ammonia, which would allow renewables to be stored and shipped as easily as petroleum products. But the current process of creating ammonia is anything but green. Combining nitrogen molecules, which are pulled from the air, and hydrogen molecules, which come from either natural gas or coal, creates massive amounts of greenhouse gases, some 1% of CO2 emissions worldwide. To make truly green ammonia, scientists get their hydrogen from water by separating it from oxygen atoms using electricity. And electricity is what renewables do best. That means regions with lots of wind and sun, like Australia, are ground zero for the new kind of ammonia production. There, the world's biggest producer of ammonia is building a pilot plant that would rely on solar electricity. The new plant will feed power from a solar array into a bank of electrolyzers, which will convert water into hydrogen. This won't produce fully green ammonia because natural gas will still be used in other parts of the plant, but it's a critical first step. Generating hydrogen accounts for half of the CO2 emissions from a standard ammonia production plant. To succeed in creating truly green ammonia, the industry will have to do away with hybrid or conventional plants altogether, and instead rely on electrochemical cells. These cells use electricity and catalysts to knit components of air and water into ammonia, all without the heat and pressure normally used to make the chemical. This isn't easy. At normal temperatures and pressures, you can produce ammonia quickly or efficiently, but not both. Now researchers are trying to create a single cell that does it all. Even if they can do it, many challenges remain. For example, scientists still need to figure out the best way to extract energy from liquid ammonia once it arrives at its destination. But if they can pull it off, this new technology could be the key to sustainable energy.
Okay. So the previous video introduced the background related to the ammonia manufacturing process, and that is invented by the German chemist who won the Nobel Prize during the first decade of the 20th century. And that is what we use to produce ammonia. And if you look at the chemical formula to the ammonia, they have 1N3H. So you can, assuming this is a hydrogen carrier, so you can also use it for transportation purpose. So the following slide showing us when we do the experiment on the left-hand side is burning the ammonia. If you look at it, it's a yellow or orange color. So compared to the right-hand side, we're burning the propane. So the color of the flame related to the temperature also related to the combustion efficiency. So the blue flame is more favorable. If you cook the food with a blue flame, it's really tasty. So the left-hand side also indicating the flame is not really stable. So the ammonia is difficult to burn. So we have four different challenges to overcome. So for example, you need a higher ignition energy. Another one will be lower flame temperature, lower flame speed. The last one will be they have really narrow burning equivalence ratio range. So this is what we can do to enhance ammonia combustion. So the ammonia combustion, I talk about it here, is trying to apply it to the power generation, thermal power generation, and also for propulsion system. So this is one we identified 5 different ways trying to enhance the ammonia combustion. For example, you can increase the preheating the ammonia before you burn it, or you increase the combustor's pressure, or you can blend it with a different type of fuels. For example, you can blend it with hydrogen. So you burn it, you have nothing, no carbon dioxide. So this is one. The most recent way is more effective to reduce NOx emission and also enhance ammonia combustion will be apply the plasma to the flame. So you apply the electric field to the flame, you can at the same time increase the ammonia combustion efficiency and reduce the NOx emissions. So that is a graph showing us. I'm running out of time, so this is a combustion occurred with a different mode. One will be with the flame. So what we observe from the experiment is showing us the flame mode. There's another one is a non-flame mode, it's a detonation. So for the defense purpose, we trying to create the next generation engines with a detonation. So the flames can be further characterized. I'm not going to introduce anymore. So this graph is showing a recent experiment trying to enhance ammonia combustion at the same time reduce the NOx emissions. So this is a very effective way. What we do is providing secondary air injection, and we burn ammonia in multiple stages. So that is how we can get it done. This figure is showing, so you can look at the values. So we can reduce the NOx emission by 50% or even 60%. So that is the conclusion of my presentation. I'm briefly introduce ammonia combustion. Another one is, this is a concept design for the ammonia-powered aircraft. So we designed these properties and design parameters for this ammonia aircraft. So this is one. This is the last one. This is another project I have been done with German Aerospace Center, so for Singapore government. What we're trying to do is for Singapore, we're trying to do the simulation. This is the simulation results demonstrating how to safely land the large size of aircraft. And the German collaborators are doing the experiment in the airport. So what you observe from this smoke is demonstrating, so when the aircraft is landing, so they will create a counter-rotating wake vortex. So this will pose a risk to the coming aircraft for landing. So if you travel to the airport, so for the aircraft landing, they need to wait 3 minutes before the first aircraft landed, and then you need to wait another 3 minutes. They give the name is 3 minutes regulation. So that is the minimum for the safety reasons. So that is everything for my presentation. Finally, I would like to thank you to give me the opportunity to present in my research, and I would like to acknowledge the team members and my families and everyone here. I really appreciate you are here and listening to my presentation. Thank you.